networks and even sort of hidden populations within, subpopulations within Twitter. And I'll say more, but maybe I don't want to put that online. So he does really fascinating stuff, and he has been a real asset to people who are trying to grow their research over here in the social sciences, and we're really happy to have him as part of the Center for Demography and Ecology. And he offered today to come share a little insight about overfitting and the relationship between bias and variance trade-off, and it's something that honestly we don't spend very much time talking about. And so it's, even though it may feel sort of fundamental, this is an issue that I think we have a lot to learn from Karl about. So thank you so much for sharing with us.
Thank you for the invitation, Jenna. It's a pleasure to be here. Thank you all for coming. And the title I put is How to Think Like a Theoretical Statistician. You're welcome to say that that's wrong or something like that, and that's fine. Who's heard the word overfitting before? Is that, okay, so everybody's heard that. Who's heard of bias-variance tradeoff as a phrase? Okay, good. So I put a warm-up in here because I'm hoping that this is kind of a notion of overfitting, and this is just R code. If you have R, you can just copy this over if you'd like to follow along.
Oh, sorry, all of you should have in your inbox an email from me with this talk. With
this link, and so you should get a link to here, and then we can go to the warm-up right here. And please interrupt if there's any questions. Okay, so here's our studio, and this, I'm sorry the font is so small, I'll make it larger. And this is the code, so I'm just going to remove everything. That's still not large enough, is it? Here we go. Okay, so the first line is just removing all the variables that are currently there, and this is just a simulation with 130 observations and 100 variables. So you probably see that there's some problems already. X is just going to be this big matrix with n rows and p columns. It's just going to be filled with numbers. You don't have to worry about how, but it's just filled. And the true beta that we're going to use to simulate it is just a bunch of zeros. So there's like nothing going on, right? Nothing. And then we're going to simulate our outcome y as, so this is matrix vector multiplication, but this is just, beta 1 times x1 plus beta 2 times x2 plus beta 3. And so x is just some random numbers, and this is a whole bunch of zeros, right? So there's nothing going on here, in fact. And then we have a bunch of error terms. And now we're going to fit that linear model. I put -1 just for convenience later. It just removes the intercept. And okay, so I imagine people are somewhat familiar with how this will behave. There's no betas going on, but you have this R squared of 0.77. Right? So it looks like if you looked at nothing else, you might say, wow, we're doing good work. We have found something when in fact it's a big lie. So I think that's probably the most common notion of overfitting. This is definitely overfitting. And so I want to talk more about that, and in kind of like a more general, not just linear models, but kind of just general framework. And to understand it more, we need to talk about the trade-off between bias and variance, okay? To really get at the point. Because I think making predictions is interesting in its own right, but also it's often sometimes easier to say what we want. I like thinking about these things in terms of making predictions. And so we can look at this model in terms of how big are the errors. And so if you're familiar with R, this is just the mean squared residual error is 27.87. That's the same thing as this. And we can then look and say, how big should that be? If we knew the true beta, how big should our errors have been? Okay, that's this thing. This is the true beta. It's a bunch of zeros. So we should, ideally, we would have estimated this thing, right? And if we had, how big would our mean squared error be? It would be 5 times larger, right? That's bizarre. It's kind of saying the same thing, that the r squared is really big when it shouldn't be. It helps to interpret these things if we don't think about trying to predict the data that we've used to fit, but we instead try and predict data that is not used to fit. And that is a really fundamental notion in kind of machine learning, statistical learning, and the notion of the bias-variance trade-off. And so here what I want to do is generate new data. Okay, so we should put x new percent star percent true beta. So this is simulating from the correct model. So this is just, we got some new design matrix, then we multiplied it by the true beta, and we added, that's not how big our error was. It was 10 times that. 10 times. This model is identical, this data is identically distributed to the data that was used to fit the model. Okay, it's just like a brand new observation. And what we now want to do is compare the optimal, the true estimator, if we had in fact observed, or were able to compute or estimate true beta, versus our fitted version. Okay? Because right now it's kind of weird that the error is smaller. This is kind of weird. But if I were to ask, if somebody were to ask you to explain what do you mean by overfitting, that's kind of, okay, I imagine like I'm an intern and like I know that somebody's overfitting, but how do you try to explain to a bunch of outsiders that like you're overfitting and like it should be this, but your model's doing this? Like they're gonna look back at you like, yeah, of course it is. I want a smaller error. That's better, right? This should be smaller. Why are you telling me that I should have a bigger error? I want a smaller error. So how do you explain that, right? Like, what is the fundamental notion? And the fundamental notion is, imagine getting brand new data, and here is y hat. So we have the new design matrix and our fitted beta hat from before, which is overfit. Okay, and now we want to say, what is the mean squared prediction error of that thing? Okay, and now remember that if we put the true beta in there, it should be something like 125, right? So is this thing going to be smaller than 27? Between 27 and 124, or bigger than 124 when we execute this line? So there's 3 choices. Is it going to be smaller than 27, between 27 and 124, or larger than 124? Of course, there's random variations, and we can do this a few times to make sure. But do you want to vote? Talk about it with the person sitting next to you. Please. It's really, this is like fundamental. And if you don't get this, if you don't understand what we're talking about, you're going to miss it. So please turn to the person next to you and check. We are making predictions on unseen data. Are we going to have less error than our fit before of this order where we had the true beta, or is it going to be bigger than that?
So just generate a bunch of X. Okay.
There's somebody sitting right behind you that's looking for a partner. He's also looking for a partner, it looks like. Do you guys get it? Okay.
Whereas it should be higher. Right, because our x's don't really have any predictor. So when we now draw a new bunch of x's, I'm reasonably sure we're going to find is that our model knows worse than the model of zeros. Because it was just fitting the random noise from before, and now we're running those different. And so
or it averages out to be the same?
it's going to be about the same. I would have thought larger, maybe.
So this is kind of the distribution if you had the true beta. 127 turned out to be quite large, so there's a distribution around, but this isn't answering the question that I asked, just seeing that if you had the true beta. So now is this last line going to be bigger or smaller than that? Okay, who thinks it's going to be bigger than these kinds of numbers? Raise your hand if you think it's going to be bigger. You're making worse predictions than the true model. It's like a lot worse, right? Like not even close. So we can do a couple simulations and see that that's 5 to 6 times worse. And so what does this help us understand? It means that we know that the R squared number is wrong, but how do you convince somebody who's unconvinced, that like doesn't understand what we're talking about when we talk about overfitting? What you need to do is you need to talk about data that's unseen. Right? You need to talk about, imagine getting more data and now trying to make predictions about that data with your current estimate. Right? That is precisely, I think, the easiest notion of overfitting. Okay. Are there any questions about this? And I'm happy to run the simulation a different way if people, we can put, for example, one fun thing to do is actually put, it doesn't matter if there's true beta or not, you get the same phenomenon. So if beta is in fact, if there is in fact something going on in beta, so here we've made it that there's actually a true thing in beta, you still get this phenomenon that your predictions,
Sorry.
it's okay, that your predictions are just absolutely horrendous. Okay. Any other questions? Any other things people would like? I could fix n and p to be something different. Should we try that? Would people like to see that? So this is overfitting. How do we make, oh, here's a good question. How do we make this not be overfitting? Fitting the linear model. How do we make that not overfitting?
Reduce p.
Reduce p. That's one way. Okay, so let's make p. What should we make?
That we use.
Yeah, so what should we make p? 10. How about 10? Yeah, that's better. Now these numbers, this one is always going to be small. Well, I shouldn't say always. Up to random fluctuations, this one's always going to be smaller because that's the true beta, right? Like that's something you never get in practice. So it's always going to be making better predictions than what you're able to estimate. But it certainly makes this is no longer 5 times this number, right? So that's one way. Another way is to make n much bigger, so we could make n 13,000 instead, and that also works. Okay, so I think there's rules that like p should be, oh, that's I did the fraction wrong there. Like n should be like 10 times p. People like to say that. I don't know. That's not a real thing, but you know that it gets better here. Are there any questions? Okay.
So I guess I do have a quick, because I have heard that rule of thumb, the 10 times. So if that is not a real thing, then what do you go by?
I mean, everybody, we need rules, right, to like do something. Like otherwise, you could simulate always. It depends on various things that are going on. For example, if your features are really correlated, I think that you're going to want more than 10 times. If your noise level is really small, you don't need that many. So for example, here, let's do this. Let's make let's make it no noise. Or let's just make it really small. Okay?
Yeah, so I guess maybe my question is more of what's the process that you go through to figure out, if you've overfit your data? And I'm not maybe totally following everything that's been done, but, you're looking at maybe collinearity or,
I will have a constructive answer for that. By the end of this, in one word, it's cross-validation. That's how I check. That's how I check. I'm not sure if that's fit for your purposes, but that's how I do it. But for example, here we can make the noise level much, much smaller. Here, P is nearly N, and in this situation, it's perfect, right? So, I mean, the number 10 is not, it's a rule, but it's not always right. And so I want to get to why that happens. That's what I'm hoping to get to in the bias-variance trade-off. Are there any other ways that we should fiddle with this simulation? Thank you for the question. Cross-validation. Okay. So there's 3 points that I want to make today. And the second and third are all applications of this first point, point 0. Sorry, the numbering's not 1, 2, 3. That there's a trichotomy between world, data, and models. And I tweeted this out this morning, and it only has 10 likes, so it might not be true if judged by Twitter. Only 10 likes. It's got more retweets, though, than usual. Okay. Science lives in the world. Estimators live with data. And models live in your head. Okay, let's make this bigger. You guys can't see that. Data lets us see the world, estimators let us see our data, and models let us see our estimators. And so, what is an example of somebody not getting this point? The conflation between models and estimators would be not getting this point. Models motivate estimators. Models allow us to study estimators. That's how they allow us to see estimators. But models are not estimators in themselves. Another point of confusion, do not confuse your data for the world. There's lots of ways that your data is not the world. Perhaps it's a sample. There are probably biases in reporting. If it's self-report data, what the fuck can we even say other than somebody who's willing to fill out a survey? I know Nora Kate has really great answers to these questions. But the point is that we have partial answers, right? There's always this gap between what you're trying to measure and what you've actually measured. So some people have partial answers to some of those problems. The data didn't come from the model, the data came from the world, and the world is not the model. Okay. This is a little bit ranty, but I think that it helps make sense of what's going to happen later, that you should not, one way of doing data analysis is you think, what is the model for this data? And then let's fit that model. And I'm trying to separate, that you should instead think of your estimators as summaries of your data, and then a model as a way of interpreting what those summaries might be doing, okay? And once you make that disconnect between models and estimators, I think that you're more comfortable with the notion of that, you're probably not fitting the right model, and that's okay, that it's still doing something reasonable. Okay. So 2 points to help maybe clarify or not. We can maybe come back to point 0 later on. So sometimes you should fit the wrong model due to the bias-variance trade-off. And So I think that the bias-variance trade-off is like absolutely core wisdom that theoretical statisticians and machine learners and these sorts of people is like in their core. However, somehow many of our stat PhD students do not get this in their courses. They learn it along the way, and it's really hard to get it. And I feel like I'm cheating giving this to you in a tutorial. Like you should have to work harder to get this stuff. So. And a friend who's super prolific and looks really scary in the pictures if you click through, he jokes that this is the only thing he really knows is the bias-variance trade-off. It's really the only thing he knows. Okay. And so this is the core of this talk. What time?
You can go for another
half hour. Okay. And do I have a clicker? Oh gosh, I hope my clicker still works. Oh my goodness. Okay. So is this large enough? Can people see this is that okay? Yeah? Yeah? Okay. So the general setup here is that you have some outcome y, which is a function of some inputs x, some features, some covariates, independent variables. I don't like that phrase, but some people might call them independent variables, x. This, you could imagine this as being a vector or like lots of stuff inside there. And then there's some additive error term. So that's what we want to talk about. And okay, so you guys know why we're interested in this. And so first of all, we want to decompose our mean squared error. That is, well, let me say one thing. So suppose that you only have one feature, this is your y, and somehow you compute some estimate of that function, and we'll call that f of hat, or excuse me, f hat of x, okay? And so now we would like to say how much error are we making? So here's f hat of x, this is our y hat, and we're trying to predict y, so we're going to square that difference, that's the squared error, and then expectation is like the mean, it's like an average over these things. So the mean squared error, and if you do some algebra, you can see that it decomposes into two parts. We're not yet at bias and variance, we'll get there next, but you have the reducible part, which is how far away is f from f hat, and the irreducible part, which is just about the error term, okay? Now, we're never going to talk about the irreducible part, again, because there's like nothing you can do about that. It's just there. So we want to understand this error. What types of errors are we making in estimating f? Do people like, let's not talk about this yet. So after going through some non-parametric things, you might jump to parametric linear models because they're easy to interpret, and I assume that everybody in the audience has heard about these things. There's also nonlinear approaches, and we're kind of interested in when should you do something like this, and when should you do something like this, right? This is a, excuse me, that's not the fitted model. Here's the fitted model. This is a model that was estimated with these maybe 30 data points to be a nonlinear model. Here's a linear model, so it's a function of this dimension and this dimension to get y hat, and that's the surface would be the surface of y hats. Okay, so how do we decide between these two things? Okay, And for the moment, we're not going to talk about the fact that this one is way easy to interpret what's going on, that you could like tell somebody over the phone what's happening here, and this one is a little bit weird, and you want to see a picture for it. So we're not going to talk about that difference, but just the difference in like which one should we prefer to make predictions to make the problem easier to state. You definitely don't want this one. Okay, so this one is overfit, and we'll get back to that later. Okay, so this is where we kind of left off on the R code, where there's these two things, they look identical except for one letter and a subscript, which is just awful notation from the authors of this textbook. And so we're going to blame them for it, but maybe I should have changed this slide. So there's a difference. This letter right here is an R, and that letter's an R, and this letter's an E, and this letter's an E. And that's the only difference between these two formulas, okay? The first formula wow. The first formula is the fitted error, or the training error. It's this number, which was way too small. Okay? The second number is the testing error. It's testing. You've not like shown the person the exam, but you're testing them, right? And so here's the exam down here. For the testing, it's this one. Okay? That's precisely what these two numbers are. Here is y. Here's our prediction for y. We're squaring it, and we're taking an average over the training. TR is training. That's how you computed beta hat. Testing, this testing set, it's this notion that there's a completely unused, fresh set of data where you can fit your model over there and then come over here and test your model. And you can compute the squared error on the tested data set. Okay? And for reasons that you already know, this is awful. This tells you, like, if you're overfitting, this doesn't tell you, right? This does tell you. Okay, so here's an example, and we'll come back to this. We'll play around with a simulation that's kind of like this in a little bit. This is another simulation where the dots were generated from a true function, which is the black plus errors. Okay, so f of x is this, and then we add some error term, some noise. Okay, and then there's three techniques that were used to fit this. One is just the simple linear regression, and then there's two others which are splines or polynomial or something like this, a nonlinear fit to this. There's one which kind of stays close to the black line, and there's another one which goes digga 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 digga. And so the digga 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 line, that one is overfit. This line, which is kind of like inflexible, is underfit, and this middle one is the Goldilocks curve, right? It's just right. So we see that, right? You can see that in that picture. In practice, you would never get this black line, and so you never know, right? Well, you can figure it out, but like, how are we going to figure that out? And so to get there, we're going to do another thing, which we still can't quite do in practice, but you can get close to it. So there's this notion of flexibility in these fits. It's actually something you can kind of crank, okay? It's like how many polynomial terms you want to include in your linear model or something like this, or how flexible do you want your spline to be in this one-dimensional case. If you had more dimensions, then it would be like, how many variables do you add to your model, right? That would be the flexibility, okay? But as flexibility increases, This dotted line represents the irreducible error. That does not depend on how you fit the model. There is always some underlying epsilon error that you will never be able to explain. And then there's two lines. This one is the training error. That's this one right here. The one that's no good. The one that doesn't tell you if you're overfitting. Okay, the training error, it dips below the irreducible error, right? Now you don't know the irreducible error in practice, but like I'm telling you, like you should not be able to explain that, so that's cheating, right? It's lying, it's a big fat lie. That's not the error, that's the training error. The other one is the testing error. This is this notion that there's some held out data set. Let's evaluate on that held out data set and see how big our errors are. And this one, notice that it picks out the Goldilocks curve, right? This is a blue dot corresponds to the Goldilocks curve right here. The digga line is way down here. It has, if you were only looking at fitted error, training error, your boss would be like, that's the one I want, until you show him the testing error or her the testing error, and hopefully that would convince them, right? The underfit line, you usually don't need to convince people of that, other than for interpretability, in which case it's much more interpretable than the others. Are there any questions about this? This is the clearest, in terms of the slides, the clearest demonstration, I think, about overfitting. Yes?
I actually don't know how you're measuring flexibility. What is, I mean, I know that you said, you know, the straight line is rigid. I get that intuitively, but I don't understand what that is.
Yes, so you could imagine fitting a polynomial model, so where you have...
Yeah.
Yeah?
Oh, I know, I understand, like, but what is 5 on there? What is 10? What does that stand for?
Oh, sorry. Flexibility F plus error. So that's what I mean. I mean the number of, literally what I mean is the number of betas. So the simple linear model, it's actually F plus 1. The simple linear model has two. There's two betas, the intercept and the slope. Yeah, good question. Other questions? Okay, so another example. The Goldilocks curve can change. So here the black line is nearly linear. And so you see that the linear curve is nearly as good as the Goldilocks curve. And this one, notice that the scale of the y-axis is much larger, and the points, the error term in absolute is the same amount, but it looks much closer here. And here, the Goldilocks curve is more flexible. Okay, goes over to the right. Okay, so yes,
Sorry,
please.
Maybe you're going there, but here the one that has 20 polynomials or whatever.
Yeah.
Is because the relationship is pretty close to the Goldilocks curve. Would you argue that the degree of overfitting is not as extreme as two examples ago?
I think of the degree of overfitting as the gap between these two things.
Right, exactly.
And it's hard to tell because the scale has changed so much. So right here it's 2.5, and here it's 20. So it's hard to.
Thanks.
Yeah, sure. Okay, so bias-variance trade-off. Suppose we have fit a model f hat. That's some curve. It's you fit some high-degree polynomial, if you want to imagine it that way, to some training data. And then we have a test observation drawn from the same population. So this is like a testing observation. So here, this is the test observation. Here's f hat, put in the x variables for that test case. We're going to square it. So this is the squared error, and this is like an average, the expectation over that. So this thing, before we had it decomposing into reducible and irreducible error, right? This is the irreducible error part over here. Now we've decomposed the reducible error into two components. The first of which is the variance of f hat at x, and the second of which is the bias of f hat squared. Okay, so what is, the parentheses here are not good. So the bias of f hat, don't worry about x0 here. This is, so let me, if you have concerns about this is a function and that's weird, just pick one value of x0, say it's 20. Okay? So now we're going to evaluate the value of this function f hat at x0. This is a number, right? It moves up and down, right? That thing has a true value f of x0. That's the black line, right? So now, why might it be that the expectation of f hat is not precisely f? That's really weird. Like, every estimator that you've seen probably is unbiased. Like, it's just totally bizarre to think of an estimator where as you get infinite data, you still don't get the true thing, right? That's what bias means. It means that if you had infinite data, you would still not get the true thing. Okay, so that's what bias is. We'll talk more about this in 1 second. I'm going to give a visualization. And then the second bit is just the variance of this thing. How wiggly is it? As you get another sample, how much does it wiggle? Okay. And so this thing, sorry, so the testing error decomposes into 3 parts here, and so now we can look at what those things are and add them up to get the mean squared error. So the irreducible error is, again, the dotted line. So that this figure corresponds to this simulation. We're only going to talk about this one, so imagine this like a little bit of a sine curve or something in there. And so I showed you this curve before, and we said that that was the Goldilocks for that sine. Now we can decompose as the number of polynomial terms that you include the bias, the variance, and the irreducible error, and they should all add up to this. So the irreducible error is here. This is variance, and this is bias. As flexibility increases, they move in opposite directions. That's kind of like the thing that reoccurs everywhere, that somehow you have some tuning parameter, number of terms to include in your model, whatever it is, and the more terms that you include, somehow the more flexible your model is, your bias goes down. Okay, in the notions that we're talking about bias here. Your bias goes down, but your variance goes up.
With respect to the training, the testing set, the validation set.
Right.
Yeah.
We have to be a little bit careful. We're talking, that's how we're going to measure it. These things sum up to this, but in practice, like you don't get to see this decomposition in practice. In fact, if we knew what this thing was, that would really help a lot of things, but we don't. If you do cross-validation or test set validation, you can see the sum of these things, and you can find where the Goldilocks curve is, but you don't necessarily, it's not so easy to then say what component is bias and what component is variance. Right? You can compute this term. Suppose that you just the simplest way is you have, half of your data over here, you fit your data here, and then you have a test set over here, and you compute your test error over here, and you do this for all sorts of different models, and so you can get this whole curve and then find that point, right? You can imagine doing that, but then decomposing in how much of it is this, how much of it is this, and how much of it is this, that's going to be really hard. Okay. Please.
Going to 2:15, I'm sorry. So you have plenty of time.
Oh, I do. Okay. Okay.
Just
Okay. Then
really, you can go.
that's totally fine. That's totally fine. Why is this not going smaller? My goodness. Why is this not getting... Why is that not doing it? Okay. So here we're going to play with this simulation. This is at the bottom of, if you want to follow along, it's at the bottom of point 1. Sometimes you should fit the wrong model. The last thing is play with this simulation, right before bullet point 2. And I give some directions to us. Okay, to play with this simulation, execute every line of code. Then you can repeat it using only the last line. So we're going to execute the whole thing, and it's going to tell us some things at the bottom then that we should do. Zoom in. Oh, gosh. Okay, so this should look familiar. This is very much, I've tried to make this very much like the first example that we had in the slides. Okay, where that is the true curve, and I've added my own random points to it, and so we can do this. The reason to do that is that now we can sample new points, okay? And you can imagine getting brand new data from that experiment or whatever gave you that data, right? Okay. And now I'm going to add just the orange line to that. And we can see how the orange line changes as we resample the data and refit the curve. Does anybody see the orange line changing? A little bit, right? A little bit. It moves up and down and it kind of pivots. Okay. Then the blue line is the Goldilocks curve. Let's not do that one just yet. Let's do the I think this is the overfit one. This one is much more easy to see how it wiggles, right? As you collect new data, the line just wiggles all over the place. Okay? And now we're going to show the Goldilocks curve. The Goldilocks curve wiggles kind of like in between them, right? We can put all three of them in. So the orange line is never good, but it's not that variable. It doesn't change that much from each simulation to the next. You see that? The dark green line, I'm going to try and convince you in a little bit that it's unbiased, but it's highly variable, right? You can easily see the variance from one to the next. Okay, now I have to remember how we do this. Okay. I think I just do that. So now I'm not going to plot the new observations, these data points. Imagine that is already happening, and then I'm just going to plot the lines, okay? And so we can kind of compare what happens. Okay? Does everybody see what happened there? And now we can do that a lot of times. See if that's too many. And so what we see here is that if you average over a whole bunch, here we've done 102 lines, you get something like a distribution of this f hat, of your estimate, right? And in the middle of that, of this thing, is the true curve. That is the notion of unbiased, right? That like, as you have a lot of these curves, the true curve is in the middle of them. Of course, in practice, you only get one, right? So you can't do that, but that's what unbiased means. This curve is horribly biased. It's not biased right here, and it's not biased right here, and it's not biased right here, but basically anywhere else. Here it's like maximum, here it's like maximum. It doesn't matter how many observations we're going to get, this is always going to be off here. That is biased. The blue curve is like it's the Goldilocks thing, right? It's in the middle. It has, you can't see it, but it is more variable than this curve. This blue line is it's kind of overplotted with this one. Actually, let's do that. Let's not plot the green one. If you kind of squint, maybe you can see that this thing is a little bit wider than this. That means that it's more variable. It suggests that. But it's also unbiased, like the dark green thing. Does that make sense? Okay. So that's the bias-variance trade-off, that you, as a data analyst, get to choose how flexible your model is. You might not be in the setting of, I've made this in one dimension where you only have one feature, and we're talking about like how many polynomial terms do you add, but this notion of flexibility is very general in terms of getting back to your question earlier, like when do you use 10? There are things that go into flexibility. It's all in the context of, it's not merely the model that you're fitting, but it's also about things like sample size. Error. What are some other ones? Sample size, size of error. Oh, no. So if nothing else changes, but you get a whole lot more samples, things which were used to be too flexible are now perhaps of appropriate flexibleness, okay? As the error term goes down, a similar thing happens, right? Having more sample is very much akin to having a smaller irreducible error. Collinearity is this weird thing that's kind of like these also, that you don't want collinearity, right? It adds to variance in the same way that having too small a sample size increases your variance, or having an underlying error term which is too high adds to variance. And the number of features, right? In the denominator of the sigma hat squared, you have n minus p. That's why, you know, something like number of features is in there as well. it's easiest to visualize these things in terms of some underlying flexibility, but all of these things could also be very much akin to the x-axis, to the 3 different lines here. We could pick the blue line or the blue model that we fit there, but then do it with a sample size which is too small and too big and just right, you know? Or similarly with the error terms. Are there any questions about that? It's a lot. Okay, that's the hard part. Oh, good, it's working now. That's so strange. Okay, so the first point is, recall, it was to separate the notion of your data and your model, that those things are separate. You don't know what the model is. Don't worry about what the true model is for some period of your time, but think about instead how is the best way to summarize this data, okay? And you want to do that in a way that allows you to study the world, not necessarily your model. Okay, so the last point is your estimation code will probably, I'm assuming, I mean there's some cases where this is not true, but your estimation code will run even when your modeling assumptions do not hold. So in your skeptical stance, I imagine we all have like different modes of thinking, and as a grumpy statistician, this is my home, this very skeptical stance. Do not consider parameter estimates as necessarily related to the model. So when I write this model, it's easy for us, it's like for our mind to see what we're doing, right? But for some time, don't necessarily think of beta hat as an estimate of this model, and this model is, the world. Instead, think of these things as merely trying to approximate the data, right? I think that there's a lot that can be had from that. And an example of this would be that if you had 0-1 data, and somebody might say, well, we should run logistic regression there, you can still fit a linear model, right? Like that is, the code will still run. The code will still run. That's what I'm trying to say. And those summaries, those beta hats are not telling you nothing. And we're often in a situation, it's often not as clear as like, oh, you should just fit a logistic regression. We're often in cases where we don't know those things. And so we should instead think about how do we summarize the data that we have? How are these estimates summaries of the data that we do have? And if you really want to get uncertainty intervals, maybe bootstrap, maybe that makes sense. Another example, the sample average, I feel like I can almost teach my 7-year-old son this. Like he's so close to understanding what a sample average is. Division is like really hard for him right now, right? That's tough. But like we're really close. It makes a lot of sense, right? Like it's just intuitive. You don't need to be mathematical or something. I mean, it's just like, it's intuitive. And also, you can just see how, if you have big outliers, that, it's no longer a good summary of what's going on. Now, imagine that you were sitting in, statistics 709, 710, and somebody said, the sample average is the maximum likelihood estimator for mu if you have IID replicates of normal mu sigma squared. And then you think, well, my data's not Gaussian. What should I do? Do you see that doesn't, it's not really helping there. That model, it's not helping us there. Does that make our heuristic justification, you can explain it to a 7-year-old and it just makes sense? Does it make that justification any less justified? Does it remove justification because you also have this weird model that justifies it in another sense? And I don't think, that's just a nice thing to say about the sample average, but that's not what I think about when somebody says, let's compute the sample average, right? And I don't think you do either. And what I'm trying to convince you to do is not just do that for the sample average, but instead try and think about linear models that way, or whatever model that you're fitting as doing something like that, as something like the sample average. It's merely a summary of the data, right? And you can use models or simulation to understand how those things behave under some random generation of the model, or some random generation of the data from the model, but you don't need the model. It just helps you see what your estimator is doing. That's all I have. I ended on time, the first time that you gave me. If there's any questions, I'm happy to answer questions. Yeah.
So is the process you use here, so I've got a data set, I want to build a model. Do I randomly select half of the data to be my training data set, half to be evaluation?
Right. I totally balked on this. I said I was going to say cross-validations, and then I totally abandoned it, didn't I? All right. I will post slides to what I'm going to go to next, but in the interest of time, I'm going to jump right to cross-validation. Who knows what cross-validation is? Who's heard of that? Oh, good. So some people have. This is what I use. It's kind of in the same neighborhood as the bootstrap and also as permutation tests, if you've heard of any of these things. All of these techniques, there's something like you have your data and then we're going to somehow shuffle it up and pull out random things and then recompute some stuff. For some reason, there was we want to observe the world as we think it might have been generated from something like that. But for different purposes, for 3 different purposes. So permutation tests, if you've heard of those are typically for testing null hypotheses. Bootstraps, you can use them for testing null hypotheses, but it's often, I think of it as generating confidence intervals. And cross-validation is to estimate the mean squared testing error, the one that you don't just get from the output, okay? Compute testing error, okay? But it's not a good estimate. This is a weird thing to talk about because now we're trying to estimate. You typically talk about estimating sigma hat squared or sigma squared or betas or mu's. Here we're trying to estimate a summary of our model, which is the expectation y nu minus x nu beta hat squared. This is the thing that we want to estimate. Right? That's like a number, right? That this expectation is this notion of going off and recreating your experiment somehow, or gathering new data from the population, sampling it. Okay, so why is this validation set approach no good? There's some randomness that goes into this. Okay, that alone is not good, but okay, you can imagine doing this randomization 10 different times. Okay? Some of the time a point is going to be over there, some of the time it's going to be over here, and you just keep going, right? And you do it 10 times, and here's degrees of the polynomial, this flexibility, and here's the mean squared error. And if you do it 10 times, you get 10 different curves. And, okay, now this is going to it's thick, and I'm sorry, it's hard. There is both bias and variance in these curves. Okay, so this is a different notion of bias and variance, but we're trying to estimate this thing, and whenever you're trying to estimate something, there's usually some bias, there's usually some variance, okay? And so we can see the variance. The variance is easy to see here, right? That those lines are not the same. Let's peek ahead and look at what cross-validation will give us. I'm not going to tell you what it is just yet, but it's going to be much prettier, right? It's going to be like that, right? That would be much better because it means that somehow that randomization, it didn't matter, right? It just did it good. Okay. So that's the notion of variance, the spread. What is the notion of bias? Does anybody know the notion of bias here? Forget about everything I've told you today. What if when you walked in the door, I told you, I'm going to tell you the benefits of throwing away half your data? What would you you'd turn around and walk out of here, right? It's totally nuts. Why is that totally nuts? You're going to get an awful model if you only use half your data, right? This awful model, not awful, but it's going to be not as good. And because it's not as good, it's not going to make as good of predictions. And so if we had used all of our data, 392 instead of 196, all of these things should somehow like get smaller, right? That's the notion of bias. So we have two problems with this thing. It's both, it has a lot of bias because we've thrown away half our data. We don't want to throw away half our data, and it's variable. We'd like to like just do it one time and have something which is good. Okay. Yes, please.
So you can shut this down if you prefer. But one of the things I was thinking about is that some of the projects that I think about when people in the room are working on, I mean, is there a point at which, I mean, a lot of these people are demographers. They use data with hundreds of thousands of observations. At some point, throwing out half your data, I mean, yes, there is a reduction, but like, so now I'm going to use 350,000 versus 700,000 observations to come up with a model.
Yeah.
So, I mean, does that change? I mean, I realize that in a theoretical sense, no, but like in an applied sense, does that change how I should even be, the extent to which I should be thinking about this way?
If you have a lot of data and all of these other features are like pretty good, you're not, for example, doing small area estimation where like, all of a sudden you're only looking at 30 samples, right? If you don't have a lot of error that's like, there's this really weird, hard to estimate thing and the error is massive and we really need, like you're doing deep, I know you're not doing deep learning, but like if you're doing deep learning, like you need millions of data points, right? You're not doing something like that. So the underlying flexibility is not that bad. Your error might be quite large. This one you might have some collinearity. You might have a lot of features, right? This would be like small area estimation where you have one for every county in the United States or something like that. It's all in the context of these things. Yeah. But certainly, if you are in the context where you have a lot of data, this might be fine. And in fact, you might not even throw away half your data. You might just throw away 10% of your data. Right? And like you're still averaging over 10% of 700,000, and so that's still a huge sample size, and you're not going to get this variability here, right? The variability here comes from you're taking an average over these data points, and as you have more data points over here, that average is going to be really good. Yeah, that's a good point. Okay, so yes, please.
So my question concerns the Iid assumption in simulation.
Yeah.
It seems to me that intuitively it should hold, or at least the assumption will continue to be that it will hold. So if you could talk about the scenarios in which we should not assume Iid in simulated data.
Yeah, so everything that I'm saying, I'm just imagining that the data is independent. You have independent samples. If you do not have independent samples, you need to do something which is more parametric and like models that dependence somehow. It might be helpful if you gave me a little bit more detail about the type of dependence that you're worried about.
So usually the data that, the assumption is that it's Iid observations and variables are, random variables are Iid, independent of each other. But then once we use the simulated data, in the course of the process of simulation, what happens to the Iid assumption, that's what I'm trying to get at. It's not that big of a concern, but then
I'm not sure that I understand. So if you, in the course of the simulation, maybe we can talk about it offline. Sure. Is that okay? Yeah. I need probably some more help understanding. Okay. So we were talking about this, which we could call test set validation, where you just have one test set. This is k-fold cross-validation. Here it's 5, k is 5. Imagine that you have 5 buckets, and you have your n data points, and so you take one data point at a time, and you just randomly throw them into buckets. uniformly at random, okay? All your data points, so now you have like roughly 20% of your data here, roughly 20% of your data here, and so on. Now, take the first bucket out and put it over there, and it's going to be our test set. Okay? Use these 4 buckets to train. Use those 4 buckets over here, you fit your model over here, and then you go over to that one, this bucket of data over here, and you then fit it, or you evaluate the prediction error over here. Okay? Then you take this bucket back over here, and you take the second bucket of data, and you put the second bucket of data over there. You fit over here on buckets 1, 3, 4, and 5. Okay, and then you repeat this process. Okay, so now you have 5 estimates. And you just take the average of those things. Okay, that's all this is saying. It's an annoying formula, but that's all it's saying. Here again, on every fit, we're throwing out 20% of our data. Right? Not half, but we're still throwing out data. Now, maybe if you walked through the door and I said, I'm going to say only throw out half, or only 20% of your data, maybe some of you would have stayed, but like, it's still throwing out data. So the farthest that you can take this is setting k equal to n, which is n-fold cross-validation, or just leave 1 out. So you just take 1 data point and you throw it over there and you fit on all the data that's here. Now, if you have 700,000 data points, this is totally ridiculous, and you're going to, you're going to melt your laptop, like the screen is going to melt off by the time this thing is done. Yeah, so that's not the only problem, that it takes a long time to run. But it turns out that if you have a linear model, you can get that thing in a closed form expression. You actually don't need to do all of the simulation. I think that Grace Waba, who's here on campus, she and somebody else, they discovered this formula, which is really, if you've heard of leverage scores, those are the leverage scores down there. It's amazing. And so this works for a lot of different things that it should be in R, and I'm sorry I can't think of the R function, but LOOCV. This is kind of an awkward point, but it typically doesn't shake up the data enough, and so the fits are highly correlated, and so when you average over these n error terms, they're not independent, and so they're highly correlated, you have more variance. It turns out that like choosing k equal to 5 or 10 is actually a better choice. And this is a variance argument. So the bias argument is only throw away 1 data point because we want our fit to be really good. The variance argument is that if you do this, then all of the f hats that you have are really similar, and these evaluations of the error are correlated with another. You add to variance. So in terms of bias-variance trade-off in estimating this thing, people often do 5 or 10 cross-validation. Okay, and so here's this picture where you can imagine doing this randomization a whole bunch of different times, but now the curves are very much similar. There's still some variability due to this randomness, but okay. That's cross-validation. Yeah. Oh, and we can then say, like, going back to these curves that you saw before, you don't want to actually minimize this thing. This would be like the cross-validation curve. If it's flat like this, go over to the left. You have to want to go like up in here. It's just like a heuristic. Okay. Any other questions? Yeah.
So, in all of this, the way that you motivated caring about bias-variance trade-off is your prediction error being large.
Yes.
I think in a lot of statistics applications, at least
right.
in my field, which is economics, often they only care about
right.
the parameter estimates and specifically
right.
being able to interpret that, right?
Right.
And like you pointed out, if you use a spline or even like a random forest or something, you get no interpretability of estimates.
Right.
Because all it cares about is mapping the data to a good prediction, right? So
right.
how much of this, like, do you think bias variance, like caring about this sort of trade-off matters when your application is only with that data set and not in prediction at all?
Who's heard of ridge regression? Raise your hand if you've heard of ridge regression. So just so everybody. So this is residual sum of squares, OLS regression. When you type in LM, it finds the B, that's a vector here, this would be a vector and this is a vector, that minimizes this thing. Ridge regression goes a little bit further and it says, J squared. We're going to add this penalty term. Okay, and this looks totally crazy at first. If you ignore this, how do you minimize this thing? Well, you set all of the b's equal to 0. All of the betas are equal to 0. That minimizes this thing. You can think of this as related to flexibility. When this is 0, that is a maximally flexible model. So if you wanted to make it go the right way, you could maybe do 1 over lambda, or let's say 1 over f. Sorry, 1 over flex. So if flexibility is really big, if you want a really big flexibility, that makes this 0. Okay? If you want a model that's kind of like this, that's not so flexible, you can set this to be very small, in which case this is very big, and then you're going to focus more on making your parameters closer to 0. Everything then goes through for trying to estimate beta with this. So on the x-axis, you have this flexibility as it's defined here in terms of ridge regression or lasso or any other penalized regression technique. And on here, you could just pick some element of beta and say, how good am I predicting that element? Estimating that element. Okay? And if this thing is really big, if this is really big and you're maximally flexible, you have a hugely biased estimator. You're just estimating 0. That's like totally nuts, right? But it's not variable. You give me more data, I'm still giving you back 0, right? And in the same way, you have this notion of bias-variance trade-off. Does that make sense? Yeah. And so another thing that you can add in here is penalty. Cross-validation. I'm serious. Yeah. And so then it gets tricky because now you're trying to go between prediction of y and estimation of beta, right? And we often want to conflate those two things because it feels really similar, right? If you get the right beta, then your predictions are the best they could be. But it turns out that BIC, if you're familiar with BIC for choosing a model, is more focused on getting the betas right, and AIC is more focused on getting the y prediction of y right. And so if you're doing cross-validation, you're doing something more like AIC, and that tends to kind of like over-select. But it's good for predictions to over-select. Okay, so this is like this fuzzy little area that you maybe care about or don't. I'm assuming people have seen AIC and BIC yeah.
Maybe I can kind of follow up with that and say, is there basically a way to choose the trade-off between, I guess, in some sense, the degree of complexity or degree of flexibility can make the parameters less, I would say, informative in some kind of regard. Like, for instance, if I have just one beta, then I know when x increases this amount, y increases that amount. Like that model, like you were saying, you can tell someone over the phone, right? But I can get amazing predictions with a random forest, but there's no way, or a deep learning or something like that, but there's no way to estimate, to know what those parameters mean, right?
It's harder.
So is there a way to kind of manage that as well, or?
You do what's appropriate to the task at hand. I mean, if you want an interpretable model that you can communicate over the phone, you fit an interpretable model. I mean, baked in that, there's this notion that there's a true model, right? And like I said at the beginning, I don't believe that there is a true model. I believe that these things are all summaries of our data, and we want the best summary. And the best is not like mean squared error. It's like as a tool. As humans use them, right? And so there's lots of different reasons why we want to summarize our data, some of which is to understand as x increases, it appears that y increases, and some of which are like, I want to make predictions.
So this might be a naive question, but you've been talking a lot about flexibility as a consequence of the number of betas in a polynomial function. And I guess I'm just wondering, since we're often doing, linear regression, multiple regression, where we may have a number of betas, but it's all linear in the parameters. How do we think about the concern about overfitting, given that it might still be a line in every case? It's a great question. As you include more predictors, the number of features, I would call that a more flexible model. That it's the same notion as up here. And if you're trying to make predictions about y, it's very natural to think about that. If you're trying to if you're actually interested in estimating some beta, that's a very awkward notion, right? It's a very mathematically distant, abstract notion that we used to think about constructing the model as it makes sense. I have some graphical model in my mind, and these are downstream effects, and these are upstream effects, and I want to include all the upstream effects, and it's the true model, and so I realize that I'm saying something which is totally weird, and sometimes this is a useful stance, sometimes not. But the notion of flexibility is very much how many predictors do you have in your model. That is very much consistent with everything that I've said. Yeah. Yeah.
I've seen it sometimes referred to as kind of like the implied degrees of freedom associated with the model. And so when you have penalties, it gives you a continuous scale, and you can kind of think of it that way. It's just degrees of freedom, and that kind of is a useful handle sometimes for people to grab onto.
Yes, precisely. The penalty, it's the degrees of freedom. We could write the number of features, we could write degrees of freedom, and as Mark said, there's often a notion that relates this term into degrees of freedom. Even though you have the same number of predictors, as this thing changes, something like degrees of freedom changes with that flexibility. Yeah. Is that? Yeah. Yeah.
This goes more into the machine learning aspect of it, but how does the algorithm decide which direction to go? You could start adding parameters. You could start with one parameter and start adding polynomial terms. How do you decide which direction to take your search for this Goldilocks model?
I tend to think that time is better spent thinking about gathering new features rather than trying to best massage the features that we have, and that the difference between logistic regression and random forest, while it might be 10%, and that's a massive difference for machine learning, in an application of that's often is that really so fundamental, or would we be better off spending our time thinking about what other data should we be gathering? So it's totally punting on the question, because I like to not spend my time thinking about how can I do a lot of cross-validation. It's really painful. Which is one reason why this closed form expression for leave one out cross-validation is so handy. I said that leave one out cross-validation is not so, such a good estimator, but having a closed form expression for it, you can search through things really, this is like R squared, right? You can compute this like R squared, and it should be in the summary table, and it's not in R. I don't know why it's not. Should write an email and just complain. That makes it very easy, though, right? There was a hand up over here, I think. Was that? Yeah, Mark.
Oh, R is open source. Can't you just sum that into R?
Yeah, email Doug Bates and ask him.
He's not on R anymore. He's on Julia.
Oh, he's on Julia, right.
But there's a core team you can still in there.
Yeah, it should. It really should be in there. The adjusted R squared, I don't know. Does anybody in here use adjusted R squared? It's in there, but it should take the place of that, I think.
Okay. Well, join me in thanking Karl.
Thank you.